computer. Okay, so last two lectures were about probability, about distributions, and today we're actually starting statistics, which is quite exciting. So statistics is the study of the collection, hold on, analysis, interpretation, presentation, and organizing of data, statistical inference using data from some noisy sample to make estimates or test hypotheses about the whole population. So here we have an example of a whole population, and there's probably some distribution which describes it, but we don't have the whole population. We have a sample, we have some noisy distribution, and based on this noisy distribution, we want to make some conclusions about the whole population. So this is like the main thing people do in statistics. So being a statistician is the major part of being a data scientist. Attention, that should be 2 T's, I think. It is easy to misuse statistics. There are 3 kinds of lies: lies, damn lies, and statistics. I think this belongs to Disraeli, famous English minister, like more than 100 years ago. Anyway, statistics involves collecting, sampling the data, making different kinds of observations, visualizing the data, making some graphs, distributions, parameters, average, mean, values, errors. Hypothesis testing, like for example, here we can have a hypothesis that A and B are the same, and this will be null hypothesis. And of course, alternative hypothesis would be that they're different, and then you test the hypothesis. Estimating confidence intervals, estimating significance of observed differences, and so on. So this is what statistics is about. Well, some basic stuff, which you of course know. So if you have some observations points, data X and I, where I is from like 1 to n, you can calculate the average number, right, a mean value of your sample. You can also estimate sample deviation. This is called standard deviation. So you calculate the differences from the mean, which is calculated like this, squared, so it doesn't depend on the sign. Calculate the sum and divide by n minus 1. And square root from that. Like, or same formula is rewritten like this. So sigma squared is called variance, and sigma itself is called standard deviation. The reason why it's n minus 1 is because of numbers of degrees of freedom. So you spend 1 degree of freedom here to calculate the mean, and now you, when you calculate the differences from the mean, you only have n minus 1 degrees left. This is a very good link. And by the way, all this on my GitHub in statistics repository. So you can follow this link. It's a Stack Exchange discussing why it's n minus 1 instead of n. Okay. So sampling, resampling, and bootstrapping. So sample is a set of objects observations which were collected by some defined procedure. The elements of a sample are known as sample points, or units, or observations, or data points, or whatever. So there are a couple of links. It's actually a very good lecture on YouTube. Okay, so you have population, you take some samples from it, and for each sample you calculate some measure, and then maybe you calculate from this, for example, you calculate the mean, right? So you have multiple means, and then you build distribution of those means and calculate some other parameters. That's the approach. And again, this picture, so you learn about big population from a smaller noisy sample, right? There's an interesting approach that if you have only one sample, can you say something more than just calculating the mean? And one of the approaches is called resampling, and one of the most common ways to do it is called bootstrap. So resampling, meaning that you're collecting multiple samples, and then you do like this thing, right? Calculate something on each one of them and do something else. Like bootstrapping is the same thing, but when you resample, you can take the same value. So you pick the value and then you put it back. So in creating the same sample group, you can actually use the same value more than once. So this is called bootstrap. The values of calculated parameters usually differ between samples. We can build distributions, estimate the variability of estimates. Under certain conditions, when the numbers are big, the central limit theorem kick in and usually lead to normal distribution and so on. Okay, this we spoke about on the last two lectures. So why bootstrapping is useful? We really don't need resampling, bootstrapping simply to calculate the mean or standard error, because this we can just do from one sample, right? More or less. Or if you already have the points, you just take as many points as you can and you have distribution, you have your mean. And all you need is these formulas, right? And nothing else. But if you want to calculate something more tricky, like for example, some ratios between values, right? So regression coefficients or whatever, something non-trivial, then doing sampling is helpful. You can take sample, calculate those values from this sample, then another sample, do the same thing, and so on. So the main benefit of resampling is simplicity of computer hacking as opposed to complex math. So sometimes if you want to figure out the distribution of something which is described by a complicated formula, it's really, really difficult. But with some for loops, like hacking, you can do it very simply. And that's why people like bootstrapping. Okay, so there are two common ways to do resampling. One coming from John Turkey, who was actually a very famous person. He invented the fast Fourier transform. He invented the word bit, like, you know, in computer science, bit, byte. And yeah, you can read Wikipedia page about him. So he invented a method of resampling called jackknifing. So this is the jackknife. And the idea is you take your sample, it consists of, let's say, 100 points. You take 1 point out, let's say the first point out, so you're left with 99 points, and you calculate whatever you want to calculate from this 99 point sample. Then you return the first point back, and now you remove the second point. Now you have again a sample group of 99 points, and you do the calculations. Then you do the same with the third point, and so on. Very simple procedure. So it was commonly used before computers. But then when computers came along, people decided to use computer power to do something more generic, which is called bootstrapping. So the main person is Efron, Bradley Efron. I believe he was in America. And so it's a sampling with replacement. Data points may be included more than once in any sample. So it was published by Bradley Efron in 1979. You see the article called Bootstrap Methods, Another Look at the Jackknife. And this is commonly what people use today. Before 1980, people used mostly formulas, integrals, analytics, like manual mathematical transformations and so on. After about 1980, which is approximately when Bradley Efron worked, people just start using computers and do digital experiments to find the answers. So they just run some virtual random experiments. It's much simpler. You don't need to know to do math. You can get your result much faster. It's infinitely flexible. Whatever formulas, difficult things you need to figure out, you can just run the experiment and you'll get your result. So the name bootstrapping, meaning pulling yourself by your own bootstraps of your boots, right? So it's very similar to Baron Münchhausen pulling himself out of the mud by his own hair, right? So there are some special cases which we'll go through, like shuffling, for example, or cross-validation. We'll go through them when we come to them. Okay, one thing to remember, because sometimes it's confusing, there is a standard mean error and standard error of the mean. And the difference between them is square root of n. Can you please mute yourself? Who is not muted? Please mute yourself. Okay, so standard deviation, again, I repeat this formula, and variance is sigma squared. So this is the standard error, and the standard error of the mean is standard error divided by square root of n, right? So this is it. Okay, and this is how you calculate it in Python. Okay, I will probably not go through this again. So this is again error of the mean, and we will talk about A/B split testing. And here is an example. So you have you measure something in experiment A, and you get the distribution, and then you measure something in experiment B, and you measure the distribution, and here they intersect very strongly. So you're not sure if A and B actually equal or not. So one of the approaches is to get more and more measurements A and more measurements B. And as you do that, your error of the mean, like the mean value, will become narrow, and then you will see clean separation. So then you can say that they're different, right? Okay. So this is the first slide deck. Let me go to the second slide deck. I really, really recommend follow this link and listen to this lecture. The guy is absolutely hilarious. Jake Vanderplas. He has several lectures on YouTube. They all are brilliant. And he later worked at Google. I think maybe he's still at Google. So I'm just following his lecture. So one of the things he's saying, like, instead of using the formulas, you can just easily do simple computer hacking. So here is the problem. We are tossing coin 30 times. So tossing a coin means heads or tails, right? What is the p-value of getting 22 heads? Well, we haven't studied what p-value is, but p-value is the probability of getting this value or even more severe. So the average value out of 30 should be 15, right? So it's half and half heads, half tails. We're getting 22, which is quite severe. And the question is, what's the probability of getting 22 or 23 or 24 and so on until 30, right? So what's the probability of these extreme events, 22 or more? And we can simply run a simple Python script. Like here, we run 10,000 trials. And in each trial, we actually generate 30 tosses, right, with two values. And then so the values will be 0 or 1. And then we calculate the sum. So how many ones? And if sum is more or equal than 22, we say, okay, this is extreme case, increase the counter, right? And we just do it. 10,000 trials, each trial is 30 tosses, and we calculate the counter, we divide it by total number of trials, and we get our p-value. So in our case, it's actually about 0.008, which is, well, less than 5%. So this is extreme, but okay, this is how easy it is. So in his lecture, he goes over 4 different examples. One is direct simulation, which I just demonstrated. Another is shuffling. So this is for A/B split testing. We're comparing 2 groups to see if their means differ or not. Is it statistically significant, the difference? And we use random experiments. In each experiment, we simply shuffle values between the groups. Like here, the groups were separate, then we're shuffling. and then we calculate means in both, we calculate the difference, and then we plot histogram of the differences, and then we'll calculate the p-value. And again, so it's basically procedure like this, like, well, a little bit different. We'll see it later, like specific example. Bootstrapping, sampling with replacement, and cross-validation. Okay, we feed points with polynomial models, and the more complex models always give smaller errors, but they may overfit, right? So let's say you have 1,000 points, and you feed the model, and it may overfit, right? So how you get rid of this? Well, you take your 1,000 points, you divide it in, let's say, 10 groups of, I don't know, 100 points. And for each point, for each group, you calculate your own model. And then you compare, right? And you will see that there are differences between these models. So you will see that it's trying to overfit. So maybe you average between them, but at least you will know the degree of how they differ, right? So cross-validation is used to get to a model which is more generic and fits more or less the same way all the groups. Okay. So here is a very interesting example. We do A/B split test using shuffling, which I kind of skipped through here, but here it goes in a little bit more detail. So we have two tests. For example, let's say you have a website and people visit, and you calculate number of clicks, or like number of seconds spent on the website, and A will be the old website and B will be the new website, for example, and they look very similar. And in fact, if you plot them together, you see that they're almost the same, right? The way I actually plotted these histograms, I was not running experiments with visits. I just said, okay, suppose they're approximately exponential, but the exponents are just a little bit different. So you see, I generated random numbers using exponential distribution with a little bit different scales, scale A and scale B, and the difference is like 8, like what is 4% between them. So like small difference. So by eye, you cannot really see the difference, right? But then you ask the question, like, if they're statistically different, like how to do that? And the approach may be, so if you calculate the actual difference, you can calculate mean here and mean in this one, and calculate the difference, right? But how you estimate if this difference is statistically valid, right? And the way you do it, you start with a different null hypothesis. You presume that they're actually the same. So you combine them together, you see, you concatenate them, and then you randomly shuffle it, and you select 5,000 here, 5,000 here, right? And you calculate, so you make the split, and then you calculate this difference, right? And you repeat it over and over again, like 5,000 times. And then you can calculate the mean of the differences, and then you calculate the standard deviation of those differences, and you can estimate is your actual difference is less or more than whatever you get in this experiment. Okay, so this is like really simple. Again, it's very similar to this approach. You just count, and then you see is it different or not. Okay. So this is how you need to deal with it. Some people say when you do A/B split testing, you can use some statistical measures like t-test or chi-square test. We will go over this test later, but the problem is that all this theory about t-test and chi-squared was developed for normal distribution. And here you see it's exponential distribution. It's not normal. So standard theory doesn't apply. But hacking, just directly run the experiments and then calculating something, works and valid. So that's a good way to go. Okay, well, another example, maybe not interesting. Okay, some resources, some books. which you can follow. Okay, I'll finish here with this slide deck. And next, I want to show you some notebooks. I did it today. So let me start the Jupyter notebook in the same directory. And again, all of this is on GitHub. So you can download the whole repository and play with these notebooks. So for previous lectures, I made a notebook which shows binomial distribution. So it explains what it is. You see C of n x from n, p to the power of x, 1 minus p, whatever. This is something we did last time. Expected value is np and so on. Okay, we're using SciPy module statistics, and it has distributions in them. And here I'm using a binomial test, and so you see different graphs. So you can do this stuff. Okay, PMF, probability mass function, gives the probability that a discrete random variable is exactly equal to some value. So you can do some tests with that. So this is a binomial distribution. This is like probability of like distribution of p-values. And again, we have limited time, so I will not actually go in detail through this. You can follow this net by itself. Okay, so this is a central limit theorem. I think this I described in more detail. So we have some data, we split it in groups, we calculate the mean value in each group, and then we make histogram and look at the shape of this histogram. So here is an example. I do coin tosses. This is the distribution. And then I repeat this experiment multiple times. And then, so you see it's -1 and 1. And the mean value will be close to 0. And then I do it again and again, 10,000 times. And then when I make this distribution, it's close to 0, and it looks like a Gaussian normal distribution, right? And next thing I do, similar thing, but I use triangular distribution. So instead of two, well, delta functions, whatever, 2 bars, I use now this shape. And again, do same thing, 10,000 experiments, and I get again to the normal distribution. So it's, oh, here it's a calculation of Euler number. So Euler number originally coming from Bernoulli from compound interest. So you do 1 plus 1 divided by n to the nth power. And this, because of we don't have infinite precision in the calculations, you see it start getting closer to the E number, but then eventually it goes off. So it's not a very good method of calculation. Another way to calculate is using the Euler's formula, which is infinite sum of 1 divided by 1 factorial plus 1 divided by 2 factorial and so on. And if you follow this, you see that it actually does very good job of approximating the E. So this is good. And here again, I provide the mnemonic of how to remember number E. It's 2.7, 18. What is it? 1828, 1828, 45, 90, 45. Is it 1828 indeed? Yes, 1828, 1828, 45, 90, 45. Yeah, so this is correct. Okay, so this was for the previous lectures. And now about today. So today we spoke about A-B split test. And I talk about different distributions, different methods. We usually want to achieve distance, like if we have two distributions, let's say with the same sigma, so we want to have the difference about 4 sigma. You see, this is 1 sigma, this is 2 sigmas, and here 1, 2. So this, like usually people consider as a good separation. And the formula then, if you have 4 standard errors, then question is how many data points you need. So this is approximately the estimate of, like if S is what is S? Whatever, like you can on your own time investigate it. So here is an example. We have A and B. We have number of points. Oops. We have number of points. Oh, it says sessions. Maybe it's like a browser sessions. No. Okay, never mind. So average time spent by the user on the website, some standard time, standard deviation of this time. Okay, pretty big conversion rate. And I'm doing some calculations and getting to the difference, the p-value. So it's less than 5%. So that means that they actually differ in this particular case. Okay, I'm doing the same with chi-square test. Again, we didn't cover chi-square test yet. So, but similar thing, we get the distribution and we look at the probability of having this difference or even more severe. So about the area of under this curve. And similar for the t-test. Or here we're looking at something else, right? Here we're looking at conversion rate and okay, and what I'm doing here, or this is the example which I was showing you. I generate two similar distributions and then calculate distribution of the differences. Okay, so you can play with those notebooks. Okay, this is about bootstrapping. Okay, this is very, very simple. We generate 100,000 points, and the points have values 2 and 3, right? And so we have a sequence like that. Here I show you the first 20 numbers, and then from this sequence I take samples from 1,000 points. So the whole size is 100,000 points. So I select samples randomly, and then I calculate something from this. Probably I calculate what do I calculate? The sum and or mean value or something, and then end up with some distribution. Okay, that's what you usually expect in all these situations. And signal from noise. Okay, this is something I've done as a physicist, like measuring signals. So suppose you have a signal, and then you add noise to it. So I have the procedure make noise, and what make noise does is just generates random numbers of some amplitude around 0. So if you take this, goes from -1 to 1, and you add noise, so -1 to 1, so it's in the middle, and then we add this random noise, so we get this. Now, suppose we make many measurements like this, and I want to extract the clean signal out of this noise. And the method is we take many, many thousands of those curves and we sum them together, we average them. And you see here I'm doing this, and let's actually run it. So if I doing this, generating the random, and then extracting signal from noise. So here I'm doing 5,000. Let's say I'm doing only 50 summations. You see, it's still noisy. So let's say I do 10. Yeah, 10, well, it does it's cleaner than this one, right? But then if I add how many times I average, it gets better and better, right? And here, like, it was 5,000, right? Okay, so it's pretty clean. So this is how people extract noise, signal from noise by synchronous averaging. Okay, this is all I have for today, right? I want, so next time we'll talk about linear regression. The whole seminar will be about linear regression. After that will be logistic regression. After that, we'll talk about chi-squared and t-test and F, ANOVA, error estimation, and then we go to Bayesian, and then some like funny stuff. So all this is, you go to GitHub, you go to my account, Lev Selector, right? You go to statistics. Okay, I don't see it on the first page, so you click on repositories and you go to statistics. And you see all these files here. And then you just go code, download zip, and then you'll have all these files to explore on your own. Okay, so this is it. I want to stop the recording.